the first thing you need to understand the intrinsic motor protection, right? So this concept is basically the back EMF and how it's generated in the motor itself when it starts up, right? So in the exam, he'll probably just ask you explain the intrinsic motor protection um component in the DC motor, or he could bring any change and ask you how it will change. So in the exam itself, most of the time he'll just bring questions, ask you to calculate this, calculate that. Then he will bring a question where he say, okay, if you change this, how this going to change? And he might just ask an outright theory question, which is based on the operation of the DC motor, right? So notice, read through the slide, right? So that's theory, right? And then, well, the next one is the losses. So same thing, you have copper losses, but the difference is with copper losses, I squared R losses. So any real component in each circuit, you will have copper losses. The mechanical losses is due to friction and windage, which is the physical, like, remember, it's metal on metal. So you'll basically get mechanical losses, right? You still have eddy currents. You have no hysteresis and thingy, right? Because it's that DC motor, okay? And well, hysteresis loss, mainly, the hysteresis is not easy, right? But you will get some friction with the dipole if you're using a electromagnet for the permanent magnet side. Remember that DC, you need a north and south pole, right? So it depends on how we model your DC motor. But most of the time, it will just be a permanent magnet, just to keep it simple. So know your losses. Right, where's my arrow? Right, so the first equation, like the backbone of DC motors, is your back EMF equation or equations plural. So there's the first one. E is equal to phi and ZP on 60A. So you want to just write the flux per pole, number of poles, Z is the number of active conductors, A is the number of parallel paths. So if it's lap, A is equal to P. And if it's wave, A is equal to 2. So this is important. Right? And well, N is the rotational speed in RPM, and but to convert RPM.
Just to interrupt you, I love the little thing that Kelsey sent to remember. The laugh on wave.
Okay.
Very effective.
Yeah, like wave
Mm-hmm.
is when A is equal to 2, and Cardi B's son's, his name, her second son, his
Mm-hmm.
name is Wave. So that's
Oh,
why I remember it.
well, yeah. Well, yeah, cool. That makes sense. So, mm-hmm. Good. Nice. Well, look at this thing, man. You had to find some ways to remember it. Ah, actually cool. But I don't know about them things, so at least I learned something there. Alright, yeah. So, yeah, right here, back EMF. Well, you know this one already. To go from N to omega M, angular speed. I will you know your motor constants, Zp and 2 pi a. So you need to know this equation and all of the parameters in it. Because if you give you a parameter and you don't know what the letter is, you're cooked. Right? And well, with DC motors, there are a lot of derived equations. Just keep that in mind, right? So there's the first back EMF equation that you'll come across, the fundamental one. Then it have one where you pull out all the constants, so Zp, 2 pi and a, you pull it out, and that will be grouped under Ka. And well, the other stuff that will be left is phi and omega m. So you end up with the next equation, which is Ea is equal to Ka phi omega m. That's the second one. Yeah, this one actually more important than this one. Also, and this is the biggest hint I could give you all for DC. Anytime he give a question where he give you changes, just use the equations to guide it. So like if a question asks and it asks me if the flux per pole increases, how will the back EMF change? So I know our equation E is equal to K phi omega m. And this here is basically directly proportional to this. So you get a state, list the equation. Since the flux per pole increases, you can clearly see that the back EMF will also increase. Yeah, all the equations linked to each other. by at least one or two variables. What that does for you is that if you're going through an explanation, you can just use the equations to guide you. Yeah, but obviously know how to understand the operation, learn it by heart, right? So first two equations, need to know it, very important. Okay, guys, we continue. So you have the power torque equation, which is this one here, EA, IA is equal to TE omega m. Know that TE is the electromagnetic torque, right? So you have a EA here, you have a VT, and I go into here. It's in series, so just know the circuit itself, right? And you just keep going with the derived equations. So you have this, and since you know what EA is, you basically just plug in EA from before, which is EK phi omega m, and guess what? You can end up with our next equation, and this equation will be in terms of TE omega m, and then you divide both sides by omega m, and again I put this one. So the electromagnetic torque is equal to K phi I, but this is where everything starts from. So don't memorize all the derived equations. Yeah, just know the main one. So this here is our main one. Because from here you know what the EA values are. Yeah, so you could derive your own equation when you need to. If your memory good, you could memorize all, by all means go ahead. But you could conserve memory space by just remembering the main ones. Yeah, so far I have two back EMF equations and the power torque equation. Ah, well, the torque equation, which is this. Yeah, well, yes, this torque is before frictional windage, which is the electromagnetic torque. Right? So let's keep that in mind. Right, excitation systems. So you have DC machines, you have brushless and brush. We dealing with brushed, right? We don't deal, we don't need to do brushless, right? So you have two main type of excitations. You have self-excited and you have separately excited. So separately excited in terms of the magnetic field, you could have an electromagnet and well, a permanent magnet. And then the self-excited ones, you have shunt, series. I don't think you all doing compound. So it's mainly just shunt and series, right? And as I said, they're classified on the basis of mutual electrical connection between the field and the armature, aka each of them have a different circuit configuration. That's basically what they're trying to say. Yeah. Let's keep chugging along, right? So separately excited, well, it means that the field winding and the armature winding are supplied by separate supplies. Yeah. But the equation itself always comes from the circuit or the piece that EA is in, right? So in this case, this is a VT. So VT will be EA plus the losses across your RA resistor, which is basically KVL. Yeah, so you end up with EA will equal to VT minus IARE. You will be seeing this equation a lot. But separately excited. So two separate sources to power your field winding and your armature winding, right? That basically what it means. And obviously each of them have a different advantage and disadvantage. So shunts, if obviously connected in parallel, well, sorry, this is parallel, sorry. So shunt and parallel is the same thing, right? So it basically in parallel with each other. So now it's one source and it's in parallel, so the voltage drop across here, and well, I don't know why they bend it, but the voltage drop across here is the same thing. So the basically split it up. So if you split, you'll have different currents. So you'll have IF and IE. So just know that this is your input current, and IN is basically your field currents plus your IE current, because it's basically in parallel with each other. Yeah, and this will be the same, but it's based on the loop that you're in. Yeah, just keep that in mind. Very important. Well, series, basically same thing, you just know everything in series, right? And it's still using key VL. which is now Vt will equal to Ea plus the voltage drop across IARE plus the voltage drop across IF RF. But IF and RF is basically the same value because they are in series. So it's basically the same equation, but instead of IARA, be IARA plus RF. So these lines on top here. So this one is designed to carry large currents. So that distinguishing that one. And then this one, it basically have two things. So in parallel, right? So it is in parallel, separately excited. It's similar to separately excited based on the equation itself. That's why I'd say it's similar, right? But when you're doing your research, know the disadvantages and the advantages of each type of configuration. So disadvantage and advantage of each configuration. So, because he could bring a question to state the advantages and disadvantages of shunt versus separately excited or something like that. You never know. So let's know those. Obviously, it'll be too much to put in the slides. But let's memorize like three. And the differences between them, obviously. Cool. So we're getting into the fun stuff, right? So now we're going into the speed torque equation, which is basically motor control. The main equation we use over and over for motor control is obviously a power torque equation. That's very important. And then you have this equation for E, so you have the Vt minus IR is equal to Ka phi omega m. That will never change. And then you have your torque equation. These are the three you're going to be rinsing and repeating over and over and over and over. Right. This one here, anytime you see this, it's basically talking about Ke or Kt. So it's basically the same value. So if you see this anyway, just know it basically means Kt. Three equations you must know by heart. Okay, heavy slide, but let's go through. So I think Kelsey was asking, I'm not sure if this was it, but I'll go through. So when you do all the derivations, you end up with this.
Yeah, that's it.
Yeah, so you end up with this equation, right? This equation was basically derived to link your speed with your IA value, right? In the slides, you will have all the derivation and stuff. He doesn't bring proofs, like he don't bring proofs. He care more about you understand how the equation does operate, right? So I was telling Kelsey, this here is synonymous to a straight line. So it'll be y, which is your speed, is equal to mx plus c. So obviously this will be c. Why? Because, well, this most of the time constant, and k phi is constant, right? So it's be c minus, and you have m, and you have x, right? So it's just a straight line. Now what they did, they start off with this, and they basically split this into different sections, right? So the first section is at no load. If you have no load, your IA will be 0. Why IA will be 0? Because EA will basically be 0. Your EA and your speed does coincide with each other. So if you have no load, you have no back EMF. Yeah? Your back EMF is due to Lenz's law. So if you put a load in the transformer, for it to spin, you have to overcome your back EMF. So if you have no load, you have nothing to resist. So the back EMF will be 0. And if your back EMF is 0, your IA will be 0, right? So for no load, you have no load, IA is 0. So this part of the equation will drop off, and you'll end up with omega m. This here is called your maximum speed, or your no load speed. Yeah? So if I ever ask you to get your no load speed in a question, you're basically just using this equation here, right? Then you have this piece here. So when you actually start to load the DC motor, you end up with an IA value, because if you load it, IA will change because of the back EMF. This piece is just modeling how much the speed drops due to the load. So you have this here. So the speed is basically the ideal speed, which is the maximum no load speed, which is similar to transformers. in terms of voltage regulation, right? You're just not dividing by the speed or anything like that. So your speed is equal to the ideal or the maximum speed at no load minus the voltage drop effect due to the load. So obviously, the bigger the load, the bigger the back EMF, and the bigger the back EMF, the bigger the voltage drop, because IA and EA are directly proportional to each other. Yeah, so if IA increase, your speed will drop, which makes sense, right? Because that's how a motor does operate. So this just modeling how the speed will drop based on the increase in the load, and this here that's given here no load speed. This entire equation is literally just a straight line, but in this case it will be a downward sloping line because of this negative here. Yeah, so you're basically varying IA and you're checking to see how the speed will change. To vary IA, you need to vary EA, because you notice I have no EA in this equation here. So when you change EA, IA will change, and when IA change, your speed will change. So you're just going down the road. So somewhere I had a little, well, up here. So when the torque is applied, the motor draws currents because of the EA value, and the voltage drop appears, which is this piece here. And when that appears, the speed will decrease, which kind of expands, right? Because if the max is 5 and IRA increase, so it could be 5 minus a bigger value, so the speed will drop. Yeah, so the speed will go down. So AKA, as the load increase, you expect the speed to drop. That's why it's a downward sloping line. Right, I don't know what this was. Well, yeah, this kind of say the same thing that the top piece had. I don't know why I put it again. All in all, for this piece here, now this equation here for the maximum speed is based on VTK, right? But for this portion of the equation here, if you want to know how the speed will change depending on changes in torque, because right now it's based on changes in IA, all they did, you end up with this equation here, and this, yes, we just replace IA. We go back to that equation. You're making IA the subject of the formula here. So you end up with IA is equal to TE on KA phi, and you're basically just taking this and replacing it for IA in this equation here. And when you do that, you end up with this here. And what that tells you, it tells you how the speed changes with respect to changes in the torque. Right? So you call this a torque speed equation. Yeah. So cool. So that's basically what that line is. So when you get into the motor control is where the servers get a little more interested. So the next equation is basically relating the TE to the omega m. So all they really did here is, remember, you already have an equation with omega m from before. So remember, you don't need to do any derivations. You don't need to do all that, right? If you want to, you could look to see how they got it, but you don't really have to do all that. What they did was replace IA with VT minus EA on RA, which is basically just using the normal equation for EA. They make IA the subject of the formula, and at this point you're talking about starting torque. From before was starting speed, now you want to know what the starting torque is. So at starting torque, your angular speed, which is omega, will basically be 0. And we know at the start, your back EMF value is basically 0. So you're just going to end up with VT on RA. But this is a separate piece. But that's where I got this from. This, you just take this and just plug it into here. Yeah? Into the same equation from before, but I digress. So this is the second T equation, and then all you're going to do for omega is 0. The VT and R are going to drop off, and you end up with this. What this is your starting torque equation. A question will literally just come, find the starting torque, right? You don't need to know all the derivations and stuff. It's not needed. It's not a proof course. Okay? He more care about you knowing the equations. So most of the time, that's how it will come. He will give you values in a question and ask you, okay, what will be the starting torque? Calculate the starting torque, calculate the starting speed, all these things, right? If you want to, you could go and see what equations they use to substitute, but I mean, you really need to do all that, right? You really not needed. Okay, so the first type of speed control is terminal voltage control. So based on the equation, you're just kind of looking at it, and so this is C, and you have mx. So obviously this entire thing here is m, this is x, and this is c, and this is speed. So if let's say, if this equation here and this says voltage control, which means a variant Vt, if you look at where Vt is in the equation, Vt is part of the y-intercept. Yeah, so you clearly see in how this is the only part that would change. The gradient of the line not being affected at all. And also the value that Te at also not changing much. Number T is your x. Yeah. The Vt is your y-intercept. So that will be on this axis right here. So if you vary Vt, the y-intercept will change, but your gradient and this will stay the same. Yeah. So for different, you'll get different speeds based on varying Vt. And all you need to do is either directly proportional or inversely proportional. If you don't know, just plug in values into the equation and see when you change one how the speed will change. But if you think about it, Vt, if you increase Vt, you're clearly seeing that the y-intercept will basically increase because k is a constant. Yeah, and you're just looking to see how it changes. Alright, Vt is directly proportional to omega, which makes sense. As you increase the voltage going into the motor, you expect the speed to increase. This is the most popular one. Yeah, so what you will need to know is, obviously you need to know the equation, which is the speed torque equation right here, and you need to know the graphs for it. Sketching the graphs. Wait, we can skip this, it's just here, right? Yeah. But know this though, so what this will be in a question, it will ask you to compare the different type of voltage controls. So knowing this is important, right? Also, one more thing, I didn't tell you, but I said increasing the voltage, but realistically speaking, voltage control only works for decreasing the voltage. Okay, if you have a battery at 50 volts, you can't get more voltage than the battery have, right? So you will really use voltage control to reduce the speed, not to increase the speed. Yeah, so which is why the graph, instead of it going up, it's going down, because it start off here, and instead of increasing Vt, it decrease Vt. So if you decrease Vt, it will be decreasing the y-intercept, so the graph will go down. Yeah, and if you keep decreasing Vt, you'll reach a point of fast specific speed at the same torque. You end up with something called holding force. Yeah, which is basically at some value of Vt for the same torque, your speed going drop to 0. So it will just hold. Yeah, so you can go through the theory, but note you need to know the different type of voltage controls, the equation for it, and the important parts. The important parts of all these here is this here. Holding. Yeah. And well, it's the most popular one, suitable for reducing speed. So anytime you need to reduce speed, voltage control is the easiest one to use. Yeah. And yeah, the terminal voltage cannot be exceeded, which makes sense. You can't get more power than the battery have. But you can get less. Cool. The next one is flux, well, field flux control. Same concept, you just look at the equation and see, okay, where changing. So now you have a flux here, and you have flux here. So you know, okay, one, the y-intercept going to change, and two, the gradient going to change from just looking at the circuit itself, right? So the field current, hence the flux will vary. So you know the graph itself now. If you were to increase the flux or decrease it, so you say increase this. If it increase this, your y-intercept will drop. If it decrease this, the y-intercept will increase. Same thing here. If you decrease this, your gradients will basically end up getting bigger. But if you increase this, your gradient will end up getting smaller. So just looking at this, you can kind of predict how the line itself will look, whether the y-intercept and the gradient going to change, if the gradient alone will change, or if the y-intercept alone will change. Yeah, that's how I look at it. And from here now, since the flux at the bottom and omega on top, that is an inverse proportion relationship. So as flux increase, the speed will decrease because it's inversely proportional. Yeah, so if it decreases the flux, increase the speed. That's inversely proportional. Yeah. So how I memorize all this, I just literally just remember the equation and just math it out in the exam with the proportions. These parts here are important. So no load speed is inversely proportional to the flux, which makes sense. The slope, talking about the speed, right? The speed is more sensitive to flux variations and variation in terminal voltage, which is why they call it field flux. Yeah. Well, we know the field voltage cannot be exceeded. Well, all these things are the same. So these things here is stuff we need to remember, because yes, he could ask you to explain the differences of the different type of voltage, the different type of controls. So know these things here, in addition to the equation on the graph. Right, and the last one is about armature control. Even if I didn't know what armature control was, I'll look at the equation. So where RA is a basic variant RA, you add in a series resistance. Okay, you can subtract resistance, right? So you'll be adding RA resistance. So the y-intercept not changing because this part here have nothing to do with RA. So you expect this y-intercept to be exactly the same. But what will change is your gradient. Because if RA keep increasing, you expect the gradient to get steeper and steeper and steeper. Because if this go up, this way dividing it into will also go up, right? So RA, but based on how the graph will look, so this one is a catch, right? So since the gradient getting steeper and steeper, you're going this way. But you notice as the line gets steeper, for the same torque, the speed actually dropping instead of increasing. Yeah, because the value for the gradient getting bigger, but is getting bigger on the negative side of it. It's not getting bigger on the positive side. So it's not going like this. It's actually getting steeper, but it's steeper going down. So for the same torque, you could vary the speed. Which is what you're trying to do. For the same torque, you're trying to control, like an elevator. If the elevator get heavier, you want it to basically go up and down at the same speed. Even if it's real light or it's very heavy, you want to be able to control the speed. So for the same torque, you want to be able to get different speeds. Yeah, same concept. So you put a R add. So yes, these circuits here is a nice way to explain it also. So knowing the equation and the circuit is good. And note that for this one, you add in a series resistance to the armature, which is very impractical, but we'll get to that just now. Some of these control types more expensive than the others. Right? So the no load speed is unchanged. We notice resistance increases until the point where the speed is 0, which is again holding. And well, overall, it is inefficient. Used when heat can be recycled. So this is under special circumstances. The reason why armature and field flux is basically kind of less practical is think about if you have a motor, you can't go any motor and yank out or put in a literal series resistance into it because you don't have access to the armature ends. Like you don't have access to those things. So because you don't have access to those things, the most popular and efficient way to control speed is with voltage control. Because in an actual motor, the only thing you have access to is the input terminals, which is synonymous to the voltage that you give it to operate under. Yeah, so the most popular one is always voltage control. Right, so winding down, but going through. So this one just went through like different operating conditions, right? So in this one here, the load torque increase, so the motor slowing down. So you kind of seen it, right? So the first thing that will happen when the load demand increases is that the back EMF will drop. Yeah, because remember it's not instantaneous, so it will take time to build up, right? So the moment you increase the load, your EA will drop, and if EA drop, you're noticing that these two things are directly proportional to each other. So your EA value will drop. So just remember VT is equal to EA plus IA RA. Yeah, so if you make EA the subject of the formula, you have VT minus IA RA. So cool. So the back EMF drops. So if your back EMF drop now, what will actually happen is that the net voltage will increase because now VT minus I will actually increase because if EA drop, when you subtract these two together, the value itself will basically increase. And when that happens, the current will increase. And because the current increase, it have an equation that links the I to T. And because the current increase, then the torque or the output torque will also increase. Yeah, so these type of things is basically how he would bring the question. He might say explains what happened in the motor when if the motor sees an increase in torque. You're just using the equations to go through the explanations. How I get this? Well, you just make IA the subject of the formula. So VT minus IA RA. So basically now, if EA drop, this overall numerator will basically get bigger, and if this get bigger and divided by RA, your IA will also increase. Yeah. Oh, same thing for this one, but you can give it a read. It's the same concept, just when the load torque decreases. So basically, everything just going to swap. Alright, what I had here now. Oh, just equations, yeah. So, I mean, EA is equal to K phi omega M. So, EA and speed is basically directly proportional to each other. Yeah. So, if your speed increase, your back EMF increase. Okay, so why this important, right? So, let me say you're on the elevator. For some reason, like just say everybody in the elevator jump off at the same time. If it's not calibrated properly, the moment you jump off the elevator is going to speed up. But you don't want that, right? And what prevents it from doing that is the back EMF. It's kind of like a protection. Yeah. So in this case here, EA and speed are directly proportional to each other. So if your EA increase, your speed will increase, right? So speed increase, EA increase. Why this is important? Because some questions they might ask you what happens if the flux in the question change. And because of this simple equation, you could clearly tell if the flux decrease, EA will decrease. And EA and omega M are basically proportional to each other, right? So all these little equations here, when you read it, just think about how it will come in a question, which you will see just now. This one you know already. I can introduce it here already. Okay, yeah, so this one's similar, but just a summarized one, right? So if they change the flux, and to be fair, the most popular one he brings is the flux changes. So if the flux change, we might say it decreased to 0.6 at the previous value, or whatever the case is. So you just calculate the new flux, and because the flux change, you know EA will change. But in order to get EA, you need IA. So you calculate IA, and once you calculate EA, and well, you know EA and omega M are literally proportional to each other. So you'll be able to calculate new speed. How the question gonna come is, you will say calculate new operating speed if the flux is to change by 0.6 or whatever the case is, right? That's basically what does come. So it'll be just flux, IA, EA, speed. Yeah. So what I did when I was doing this is I kind of went on chat and I just went through the different changes. Like if I change flux, if I change RA, so just to expose myself to how the changes will look before going the exam. And he brought a flux control, which is the one in the notes. So you get through. Yeah. Cool. Alright, so I have this here. So that's basically under the equations part. So I stop it.